Hi, this video is on section 5.3. Um, so let's get right to it. This first slide is kind of a continuation from 5.2. So I would watch the 5.2 video first to understand the difference between a right endpoint and a left endpoint. So it talks about right endpoints here. I'm going to Oh, it just wanted to do right endpoints. So let's talk about a right endpoint. The difference between this problem and from 5.2 is this number here. If you look in summation, if you look or if you look in 5.2, we did integrals. We're adding up triangles from 0 to a certain number, like 0 to 2. So let's say we don't start at 0 though. So instead of summation, we're using integration, which is the same thing. Integration is finding the area. But we're not using 0, we're using -2. Remember, for the width, we used the distance that we were covering. By the way, here's the graph of this 2x. It looks kind of like this. And we're going from -2 to 1. So we want to find this area. We want to find this entire area. In 5.2, we started at 0. Here we're starting at 2. So the width, if you look, from -2 to 1 is 3. Look, from -2, -1, 0. -2 to 1 is 1. Then from -1 to 0 is 1, and then from 1 is 1 here. So we're talking about a distance of 3 between -2 and 1, and we're going to divide it by the number of triangles, like rectangles, we're going to use to find the area. So if you don't understand that, go back to the 5.2 video. This is our width. And to find the area of each triangle, it's length times width. So this is our width. And if you remember our length, we put the 3n inside of here, and then we attach an I to it because we use a summation for the number of rectangles. And we were doing a summation from I, from 1 to the number of rectangles we were using. Okay, so this is our width, and then we plug the width times I, and this is for right endpoints. We plug that in. For left endpoints, we did 3 times I minus 1 because we started at 0, but this just says right endpoints. And if you look, we're starting at -2, so once again, here's our width, and this is going to be our length. Our width is 3 over n. The distance between -2 and 1 is 3, divided by the number of rectangles. And here is our the 3n with the I for each section of the rectangle we're going to do. But since we didn't start at 0, we put the -2 here. We're starting at x equals -2. And then when we put a 1 into the I, we do the left endpoint and we draw the rectangle, and then the next rectangle, and so on and so on. So we just used a -2 to start us off here. And in 5.2, we didn't have this -2 because we started at 0. And then you just go through the process, the same process of 5.2, and we can factor out the 3n and this 2. We plug this into the function. You see the function was 2x. 3 times 2 is 6. That's how we got the 6. And we divided each of these by an n. And so they just went through the process. I wasn't too worried about the process, right? When you set n now to infinity, you get 3 and -3. So I just wanted to show you that the length it was different in these problems because we started at -2 and not a 0. So the what we put into this part of the function was a little different. So I just wanted to show that. The rest of it was algebra, taking you through the process. And if you go through 5.2, you'll see that. There's a section on the test where you have to find the area using shapes. So if I drew this graph, by the way, this function is y equals 4, right? If I draw this graph at y equals 4, it goes from 1 to 3. So y equals 4 goes from 1 to 3. So if I find the area under this is a rectangle, or the here is 2, the height is 4. So this area is 8. That's it. It says sketch this and then find the area. It doesn't say it here, but on the homework or on the test it says find the area using geometric shapes. So you would find the shape here. This is a rectangle. The width is 2. The height is 4. 2 times 4 is 8. The area equals 8. We can also do this, the method that we learned in the last section. What was it? 5.5. You can take 4 and integrate it. If you integrate 4, you get 4x. And you integrate this between 3 and 1. Put a 3 in there. 4 times 3 is 12. And then you subtract by putting a 1 in there. 4 times 1 is 4. 12 minus 4 is 8. Do you see? This is the way to do it using integration. And this is the way using geometric shapes. So there'll be one problem on the test to show you work of geometric shapes. And you have to show the area of all the different shapes and how it adds up to the answer. You have to give me the formulas and the actual shapes of this. Now in 5.3, this is, I think, a really simple section as far as the rest of it. There is a theorem somewhere in 5.3. It's the definition of two special theorems on page 311 of 5.3. If it says the A and the B are the same number, if A and B are the same number, then this integration always equals 0. If you had integration from 2 to 2, it doesn't matter what function you're using, the answer is 0. If the A and the B are the same, then the function always equals 0. You can't, think about it. Here's a shape. If I want to find the area between 1 and 1, there's no area there because there's no width. So width is 0. 0 times anything is 0. Then there's a question that says if the higher number is on the bottom, and by the way, this is once again on page 311. If the higher, you should always have the smaller number on top. You should always have the smaller number on the bottom and the higher number on top. So you can change this. If you're going to change these two position, like we did, we put the 0 on the bottom and 3 on the top. Everything stays the same except you put a negative in front of the integral. So that's the definition of the special integral that just says if you switch the spots of your A and B, like we did here, the lowest to highest, make sure you put a negative in front. That's all that tells us. And I think this is the last slide. There's a part of the homework and the test that this pertains to. They give you these things from 1 to 3, integrating from 1 to 3 x squared, they give you the answer. Integrating from 1 to 3 x dx, they give you an answer. Integrating from 1 to 3, if you had a constant of 1, they give you the answer. So using the properties of integration from 1 to 3, I can just do negative x squared plus from 1 to 3, 4x plus, or minus, this time it's a minus 3, minus 3 from 1 to 3. I can bring this negative in front, like there's a negative 1 from 1 to 3 x squared. I can bring this 4 in front, so this can become 4 integration from 1 to 3 x. And the same way with this one, I can bring the 3 in front from 1 to 3 integration. A constant of 1 then would be there. And you can put dx after each one of these. Dx, dx, dx. Now, if you look at our formula, 1, 3x squared, this changes to 26 over 3, but there's a negative in front of it, so it's a negative 26 over 3. Here, this part changes to 4. Do you see 1 to 3, just x dx? Changes to 4, but there's a plus 4 in front of it, so you have to multiply it. And then there's a minus 3 times whatever this equals, and this equals 2. So we get a negative 26 over 3 plus 16 minus 6. And then you do the math and get that. Everything changes to 3, which is 48. Changes to 3, which is 18. So this is 30 over 3 minus 26 over 3. So you end up with 4 over 3 as your answer. All right, so that's it. That's 5.3, section 5.3. If they give you these, you just use the properties of integration, where you can put the constants out in front. Any constant you can factor out and put it out in front of the integration. And then if you have the x squared like we have here, you can change that to what it equals. And then that should get you to the answer quicker. All right. I hope this video helped. It was kind of quick, but 5.3 seemed like a very quick and easy section. Except for that first part, you had to use parts of 5.2 to understand how you get the width and the length before you plug it into the function and integrate. And then we always set it, the n, equal to infinity, because you want to create an infinite amount of rectangles when you're looking for the actual solution. I hope this video helped.